Good morning, students. We are continuing with finite state machines and how we can model a finite state machine using Mealy as well as Moore. So in today's class, specifically, we'll be looking at problems based on Mealy model. Usually what kind of questions are asked in KTU exams and how you can solve them. So this is the main highlight of today's lecture. Now, let us look at the first problem. Okay. Now, design a circuit that will function as prescribed by the following state diagram. Use D flip-flop for implementation. So, any question which is related to this is solved using similar techniques. So here you are asked to design a circuit whose state diagram is given here. And they are asked to use D flip-flop. If nothing is specifically asked, you can use any flip-flop. Here they have asked D flip-flop for implementation. So, once you are given with a state diagram like this, the first step is you observe whether it is a Mealy or it is a Moore. So here this state diagram corresponds to Mealy. Why? Because states are given. Together with state, output is not written, but output is written where? It is written on the state transitions or the edges. It is written as input-output pair. So, input-output pair will be usually written in Mealy model. So, this state diagram corresponds to Mealy. Now, identify what are the inputs, what are the outputs and what are the states. Now, input is of how many bits? Look here. This is the input. It is of 2 bits. Let us say it is x1, x2. x1, x2 pair. And output, look here. Output is of how many bits? It is just of 1 bit. Look here. It is of 1 bit. You're calling the output by, say, variable name Z. It is of 1 bit. Now, what about the states? You are having 2 states, state A and state B. Okay, so this much information you can get by just looking at the state diagram. Now what is the next step? Next step is obtaining the state table. So once you are given with a state diagram, you can obtain the state table. So in state table, you first write present state, next state, comma, output for different inputs. This by x1, x2 means next state output for different inputs. It is written that way. Okay. So you first write the present states. You have state A, you have state A as well as you have state B. Okay. And what are your input combinations that you have to write here? x1, x2 is your input, 2 bit. 2 bit can take how many combinations? It can take 0, 0, it can take 0, 1, it can take 1, 0, it can take 1, 1. Now, when your see the first row, okay? When your current state or present state is A, you are providing 0, 0 as the input. Look here. What is your output? And what is the state? It will remain in state A and outputs 0. That is what is written here. It will remain in state A and it will produce an output of 0. Now, when your present state is A and you are inputting 0, 1, look here. What happens? For 0, 1 as well as 1, 0, it will again remain in state A when those input combinations are given and both will produce output of 1. So that is what is written here. When your current state is A, you are giving the input combination 0, 1 as well as 1, 0. Your state is A itself in both cases and output is 1 in both cases. Now the last one, 1 1. When your state is A and you're going to input 1 1. Your state is A, you're going to give input of 1 1. 1 1 is here. What happens? It goes to state B and outputs a 0. That is what is written here. When 1 1 is given, state A changes to state B with an output of 0. Similarly, you can do for this one, the second one. When your state is B. When your state is B, for all these combinations, 0 1 input combination, 1 0 1 1, it will remain in state B. Look here, these three. For the first two, output is 0, and for this one, output is 1. Look here, this one output is 0, this one output is 0, this one output is a 1. Now, when does it go to state A? When you're providing 0 0. When you're in state B currently, you give an input of 0 0, it goes to state A and output a 1. Is it clear? So it goes to state A, output 1. This is how you obtain the state table from the state diagram. So state table is nothing but a pictorial representation of your state diagram, or tabular representation of your state diagram. State diagram is pictorial representation and state table is your tabular representation of your state diagram. Now, what is the next step? The next step is state assignment and forming the transition and output table. So, you know that there are two states A and B for this case. So, since only two states are there, you can tell A is equal to 0 and B is equal to 0. This is how you assign values to the states, and this process is called state assignment. You randomly assign values to your states. You have only two states. So in digital, using 1 bit you can represent two states. So only 1 bit is needed to represent the states. A is 0 and B is 1. Now, this is your transition and output table. So what does this mean? In the previous slide, look here, you wrote present state, next state, comma, output for different inputs. Here you are separating that first. You write the present state, you write next state for different inputs separately and output for different inputs separately. In the previous one, they were written together. Now you are separating that. You just separate that. And then you assign value as A is equal to 0, B is equal to 1. Look here. So this one will be split to one more section. Present state, next state for different outputs will be here. Output for different states will be here. Okay. So A is 0, B is 1. So what will be the next state? A, B, A, B, B, B. Look, A, B, A, B, B, B. Same. You are assigning values after that. Similarly, what is your output? Look in the previous slide. Output was, the second one was the output, right? It is next state, comma, output. So the after comma, it is the output. 0, 1, 1, 0. 1, 0, 0, 1. That I am separating it to other sections. 0, 1, 1, 0, 1, 0, 0, 1. So I separate these two. Next state, comma, output for different inputs. I am separating it as next state for different inputs and output for different inputs separately. And then after that, I am going to assign A as 0 and B as 1. This is how I obtain my transition and output table. Now, the next is forming the excitation table. For that, you write the present states first, input combination, next state, output. All these you already have. And one more addition, you have to obtain the input to the flip-flop. So what is your present state? Present state is A or B. That is, present state can be a 0 or it can be a 1. So when your present state is 0, how many input combinations you have? 0, 0, 0, 1, 1, 0, 1, 1. Similarly, when your present state is 1, how many input combinations you have? 0, 0, 0, 1, 1, 0, 1, 1. Right? Look here, when your present state is 0, you have all these combinations. Similarly, when your present state is 1, you have all these combinations. That is what is written here. You have to write present state A is equal to 0 4 times and present state B is equal to 1 4 times for each of the input combinations. So hope this both are clear for you now. Now how will you write the next state? It's already there. Look here, when your present state is 0, input combination is 0 0. What is the next state? 0. Then 0 for 0 1. For 1 0 0. For 1 1 1. 0 0 0 1 in order. Look, 0 0 0 1 in order. Like that you can write. So I hope now writing the next state is also clear cut. It's directly from the previous table. Now how will you write the output? Output is also there. Look here. Here. So when your present state is 0, for the different combinations you have 0, 1, 1, 0. Look here. 0, 1, 1, 0. Look here. This way you are writing. Now the only part which you don't know now is input to flip-flop. All the others are directly obtained from the previous table. So how will you get the input to the flip-flop? So how will you get the input to the flip-flop means it is basically from the excitation table. You take present state combination, next state combination. This is actually like your Qn. The small y is your present state. I have given the variable as small y for present state and capital Y for next state. This present state you can write Qn. Next state you can write Qn plus 1. So this is actually like your Qn plus 1 combination, small y and capital Y. Using that, you can write the input to D flip-flop. D value you can get from D flip-flop's excitation table. So when it is 0, 0, your D is 0. 0, 0 again, your D is 0. 0, 0 again, your D is 0. Here it is 0 and here it is 1. It goes to 1. Similarly, you can fill the others. So based on your excitation table of D flip-flop, by taking the present state and taking the next state, you can get input to the flip-flop. So this table is almost complete now. Now you can obtain the K-maps. You obtain the K-maps using present state and input. Present state is small y, input is x1, x2. By taking these three combinations, you are creating the K-map for D separately and Q separately. Look here. My present state is small y. Here. My input combinations are x1, x2. Using that, I'm going to create the K-map for D and K-map for Z separately. Look here. For 0, 0, 1 in your D's K-map, it is 0. 0, 0, 0. Look, it's always good to put 0 and study, okay? Otherwise, it may be confusing for you. I don't know why they have not written. You please put zeros. Wherever nothing is shown, it is actually meaning that it is 0. Now, you form the K-map. Here, 3 pairs are formed. You can read it this way. Here, 4 single elements are there. It's actually equivalent to x1, x4, x2, x4, y. So, how you're getting this? you can take the common terms outside and change. You will get this equation. Even if you implement it this way, it is okay. But by looking, if you get this one, it's better to write this way. Next step is to draw the diagram. So, what is the meaning of this? Look this table. D. I have one D value. So, what is the meaning of that? I have one D flip-flop. So, in implementation, always draw that D flip-flop first. Your D flip-flop with clock Y complement. So, Y is your state, right? So, the flip-flop's output is actually producing the state. This Q itself is your, Q is same as Y. Don't forget that. Now, how are you going to draw the circuit? D is equal to yx2 plus yx1 plus x1x2. So, if you take y outside, y common into x1 plus x2 plus x1x2. Look here. Y is coming into x1, x2. You're providing to OR gate to get x1 plus x2 into y. So y into x1 plus x2 you got here, plus x1 into x2 from this AND gate. You're going to D. So this is how you form D. Similarly, you can form Z also. x1 you took, x2 you took, to an XOR you get x1 XOR x2. And y is coming from here to another XOR. So you can only provide two inputs to an XOR, right? So if this output plus this y is coming, it is x1 XOR x2 XOR y. That is your Z. So this is how you can implement your circuit. So even if you don't implement this way, if suddenly you couldn't solve this and make it into this equation, you can implement this. The thing is that it will be more space consuming. It will have more components and it will be some more confusing, that's all. It cannot be wrong. Now if you go to the second problem, so here also you are asked to design a circuit whose state diagram is shown here. So here also you can understand that it is a Mealy model. You are having input-output pairs and no output is written together with a state. So it is Mealy. So how many bits your input has? Just one input. You call that input bit as X, your output bit as Z, and you are having 4 states A, B, C, D. Now you form the state table from your state diagram. This will be given and you form the state table. So in present state, how many state you have to write? A, B, C and D. So you write all the 4 states in your present state. Then what do you have to write? Next state, comma, output for different inputs. Now, this is how you write. First take the present state A. When you provide input of 0, what is your output? 0. Look here, input 0. It goes to state A itself and your output is 0. When you're providing input of 1, what happens? When you're providing input of 1, it goes to state B and output 0. Look here, it goes to state B and output 0. Now, when are in your state B, what happens? When there is input of 0, your output 0, it goes to state C. Look here, it goes to state C, output 0. This is that. And when your input is 1, it remains in state B and output 0. Look here, it remains in state B, output 0. So this is how you can write the state table. Now state assignment and transition and output table. So state assignment means here you have 4 states. So if you just choose A is 0, B is 1, then what will be C and D? You can't do that way, right? You are having 4 states, so you need at least 2 state variables. So you can assign A as 0, 0, B as 0, 1, C as 1, 0 and D as 1, 1. And you form the table with present state, next state for different inputs separately and output for different inputs separately, and assign these values. So 4 states need 2 state variables, small y1, small y2. Similarly, your next state will be capital Y1, capital Y2. So this is how you form the transition and output table. So A, B, C, D, A, C, A, C, B, B, D, B. This will be your next state, and these portions will be separated out to the output. This one. 0, 0, 0, 1, 0, 0, 0, 0. Look, 0, 0, 0, 1, 0, 0, 0, 0. So this will be separated and A, B, C, D values will be assigned. So you always remember that you are having 4 states. So it needs to be represented by 2 state variables. If your output, if your states was just 2, you need only 1 state variable, small y. But if you have 4 states, you need at least 2 state variables to represent. 2 raised to 2 is 4. So you need state variables y1, y2. Now next step is to form the excitation table. You have to write present state, input combination, next state, output, also input to the flip-flops. So here, how are you getting the present state? Your present state is 0, 0. Your input can be 0 or input can be 1. Look. For 0, 0, your input can be 0. For 0, 0 again, your input can be 1. Similarly, for 0, 1 combination, 0, 1 combination, your input can be again 0, 1. For 1, 0, 1, 0, again your input combination can be 0, 1. Again for 1, 1, sorry. For 1, 1, 1, 1, your combination can be again 0, 1. So I hope writing the present state and input is clear for you. Now how will the next state and output be written? Look here. Next state is quite clear. It is 0, 0, 0, 1, 1, 0, 0, 1, 0, 0, 1, 1, 1, 0, 1, 1 in that order. By looking this, you can write. Similarly, your output also. You can write from this state table. Now, the only thing is finding the input to the flip-flop. How will you find the input to the flip-flop? You have to take small y1, capital Y1, present state, next state, y1s, and obtain D1. Similarly, take small y2 and capital Y2 to get D2. So it's like this. Small y1 is 1 here, capital Y1 is 0 here. It is like your Qn plus 1 combination. Your D will be 0. Similarly, your y2, small y2 is here. Your capital Y2 is here, 1, 0. You're getting again 0. This is how you have to fill the input to the flip-flops. So you're having 4 states, so you need 2 state variables y1, y2. Your next state will also be capital Y1, y2. And since you're having 2 state variables, it cannot be using one flip-flop alone. You need 2 flip-flops. For each state or each output, you need 1 flip-flop. So here you are having 2 state variables and you are having 2 flip-flops. So the number of state variables decides the number of flip-flops. So next step is forming the K-maps. Using present state and input, you form the K-map for D1. Similarly, using present state and input, you form the K-map for D2. Using present state and input, you form the K-map for EZ. Look here. Y1, Y2, X combination is taken. You form the K-map for D1, D2 and EZ. Please don't forget to put zeros here. Z is directly written. Why? Just see Z. If you look here, only one term is having 1. So you look the corresponding terms. In present state, y1, y2 is 1, 1 and input is x. So it is y1, y2, x bar. Look, y1, y2, x bar. Now you've got all the equations. You can implement it using a circuit like this. Here you have D flip-flops. Why? You have 2 state variables. It requires 2 flip-flop. One for y1 and one for y2. I told that in previous examples you called the output as q, but here they're just representing by another name y. That's all. You're having 2 flip-flops, so you're having 2 outputs, 2 states y1 and y2. Now you can implement the obtained expressions. Now, let us look at one more problem. Design a circuit that will function according to the following state diagram and use T flip-flop for implementation. It's again merely because you are given with input-output pair. Input has just 1 bit, you call by X. Output has 2 bits, you call by Z1 and Z2. There are 4 states PQRS. Now, you obtain the state table first. Present state, next state, comma, output for different input combinations. So, you take P first. When your input is 0, it will output 0, 0. Look here. And goes to P state itself. So, when your input is 0, P will remain in that state itself. Output will be 0, 0. Now, when input of 1 is provided, what happens? It goes to state Q and output 0, 1. Look, it goes to state Q, output 0, 1. Similarly, you can finish off the entire state table. Now, next step is state assignment. Here also you are having 4 states, right? PQRS, or you call it ABCD for simplicity. So this A is actually your P. It's actually your P. This is your Q, R and S. I've accidentally written it as ABCD. Let it be anything, okay? You call by the same variable everywhere. Now, how can you form this table? Present state, next state for different inputs, output for different inputs. You have to first separate that and then assign the values of P is equal to 0, 0. What is P? P. You can call it as P is 0, 0. Similarly, what is Q? Q. What is Q? Q you can call it as 0, 1. Similarly, R. R is 1, 0 and S is 1, 1. You finish off this table. So here the output will also be of 2 bits. Please don't forget that. Look here. Output is 0, 0, 0, 1, 0, 1, 1, 0. 0, 0, 0, 1, 0, 1, 1, 0. You fill this table. I hope it is clear to you how to fill this table. Now you form the excitation table. For that you need present states. You're having 4 states, so you need 2 state variables y1, y2. Your next state will be having capital Y1, Y2. Input, it's a single bit input, so you just need X. There's no need for X1 and X2, you just need X. And outputs, Z1, Z2. It is 2-bit output, so you have Z1 and Z2. And what about the required excitation? You have 2 states Y1, Y2. So you will require 2 flip-flops with excitations T1, T2. So based on Y1 and capital Y1, present state, next state, Qn plus 1 combination Y1, capital Y1, you find out T1. Similarly, by taking y2, y2, you can get q2, t2. So you can fill this excitation table and obtain the equations. So this is the K-map for T1, this is the K-map for T2, this is the K-map for Z. So you can form the K-map for Z1 and Z2. You will get Z1 as Y1 and Z2 as Y2 that I have not done here. Here I have taken states and input as the input of the K-map. Y1, Y2, X pair. See here all the others are 0. So in this way you can form the K-map and you can form the equations. Now you can implement the circuit. Z1 is Y1, Z2 is Y2. So what is Y1 and Y2? You have two flip-flops T1, T2. Output of first one is Y1, the output of second one is Y2. It means that the state is the output of the flip-flop. So Y1 is directly your Z1, Y2 is directly your Z2, and you have to now obtain T1 and T2. T1 is Y2X, T2 is X. T2 is X, look here. T2 is X. T1 is Y2 into X. So I hope by these three problems you are clear with how to design a circuit if you're given with a particular state diagram. If you're given with a state diagram of a Mealy model, how you should proceed and how you can create the circuit. The first step is identifying which model it is. Second is identifying the number of bits required for input, output as well as state. Next is forming the state table from the state diagram. The next step is state assignment. Next step is forming the transition and output table and excitation table. Then you form the K-maps and write the equation of inputs to the flip-flop and output of the circuit, and then you implement it. So I hope it is clear. If you have any queries, please feel free to ask me. Thank you.